Okay, so this is Chemistry 111 Practice Exam 3, Part 2, starting with question 21. It says chemical energy is the energy associated with random motion of atoms and molecules. Well, this type of energy would be called thermal energy. So this is thermal energy, the energy associated with random motion of atoms and molecules. The next one says the energy available by virtue of an object's position. This is kinetic energy. So kinetic energy. The next one, solar energy. For example, the energy that comes from the sun. This is radiant energy. Radiant energy. So the last one better be the correct answer. Chemical energy is the energy stored within the structural units of chemical substances. And we know that this is, in fact, what chemical energy is. It's the definition of chemical energy. All right, let's take a look at question 22. Which of the following processes is endothermic? So that means it is not going to release heat into the surroundings. It's going to absorb heat from the surroundings, okay, into the system. And if you look at the first one, we're going from water in the gaseous phase. So water in the gaseous phase, that's steam, right? And then it's being converted into water in the liquid phase. So that's a condensation. Well, we know if you've ever had steam contact your skin, you know that that releases a lot of heat. So this would be an exothermic process. A lot of heat would be lost when you have that steam condensing. So that's an exothermic process. The next one says we're taking water in the solid phase, which we know as ice, and we're converting it into a liquid. So this is just melting ice. And if you've ever put ice against your skin, you know that this is an endothermic reaction because the ice absorbs the heat from your body or from your skin, and it makes you feel cool. And so this would be an endothermic process. So in fact, this is the correct answer. Is B, is an endothermic process, the melting of ice. The next one is the combustion of hydrogen in the presence of oxygen. And of course, that releases water vapor, and it also releases a lot of heat. So that would be an exothermic reaction. And the last one shows the combustion of methanol. This is methanol or methyl alcohol. So methanol, which is, fondue fuel, or it used to be used as a fuel in cars in the Indianapolis 500. But anyhow, that's a combustion reaction. And so that releases a lot of heat. So those are exothermic. And I'll just write here, these are both combustion processes, right? Because we're combining something with oxygen. Okay, let's move on to question 23. It says, an exothermic reaction causes the surroundings to release carbon dioxide, become acidic, expand, decrease, or increase in temperature. And you probably know already that the answer has something to do with temperature. And when we think about an exothermic reaction, heat goes from the system, right, and it goes into the surroundings. Okay, so that's what an exothermic reaction is, right? A reaction is what we call our system, and then it releases heat. And so what that's going to do to the surroundings is it's going to have heat flow from the system into the surroundings, and that's going to cause an increase in temperature in the surroundings in that exothermic reaction. Question 24, it says the reaction that represents the standard enthalpy of formation, and we denote standard enthalpy of formation is the heat of formation, and we put that little knot symbol up here at the top, and that represents its standard conditions for the formation of sucrose. And they've given us the formula for sucrose, which is C12H22O11 is, and then it gives you all these different options here. Well, we want to end up with sucrose as our product. And if you look at the first answer, A, sucrose is not a product, so that is not an option. And if you look at C, sucrose is not an option there either. Now, if you look at B, D, and E, they all have sucrose as a product. And what is sucrose made of? If it's C12H22, let me fix that. 22O11, it's made from carbon, it's made from hydrogen, and it's made from oxygen. And so if we are talking about the standard enthalpy of formation of sucrose, we're going to talk about the standard enthalpy, which means the formation of sucrose from its elements in their most stable form. Now, the most stable form of oxygen is O2, right? There is another allotrope of oxygen, which is ozone, but that's not the most stable form of oxygen. And the most stable form of hydrogen, because it's a diatomic gas as well, is going to be H2 gas. Now, if you look at B, you can see that we have H2 gas and we have O2 gas. What else? Let's see here. In D, we have H2 gas and we have O2 gas. And in E, we have H2 gas and we have O2 gas, like that. What's the problem? You know, how do we discern whether it's B, D, or E? Well, it's going to hinge on the carbon, right? What is the most stable form of carbon? And we covered this in lecture. We said that the standard heat of formation of carbon, when it's the allotrope, which is known as graphite, is equal to 0. Now, we could put any units we want because the 0 is always going to be 0. So that's the most stable form of carbon. In the delta H of formation, or the enthalpy of formation of an allotrope of carbon, known as diamond, is actually 1.90 kilojoules per mole. Now, you don't have to have these numbers memorized, but what I did ask you to know is that the most stable form of carbon is graphite. And so the answer must be B, because it says we take 12 moles of carbon graphite plus 11 moles of hydrogen. And in every hydrogen molecule, we have 2 hydrogens. So 11 times 2 gives you 22, plus 11 halves, which is 5.5 times 2 for my oxygen, gives me 11 oxygens. And there we have it. So the answer is B. That equation rather shows the standard enthalpy of formation for the sucrose molecule. And sucrose is simply table sugar. So table sugar. Glucose is not table sugar. Sometimes I'll have a student think, oh, glucose, isn't that table sugar? No, that's sucrose. Okay, let's move on to question number 25. Which of the following processes always results in an increase in energy of a system? And when we talk about the change in energy of the system, which our book uses delta U for change in energy, okay? And I'll just write the whole word here, energy, because he uses U for energy. The change in energy is equal to heat, Q, right? This is heat, plus W, which is work. That one's a little bit more intuitive, okay? And in order for this process to always result in an increase in energy, that means that my Q is going to have to be a positive number, and my W is going to have to be a positive number. So what I'm looking for is a scenario where both my Q is positive and my W is positive. Well, I'm going to write down a couple things here, okay? And we covered these in dirty detail in class. But when Q is positive, and this is just a little shorthand I use for positive, heat is gained from the surroundings. So heat is gained from the surroundings, and of course it goes or flows into the system. So that means we have a positive Q. So if we look at the possible answers, the system gains heat and has work done on it by the surroundings, so that's definitely a possibility. The system loses heat. You can see that the next two have loses heat. That is not an option because we have to have heat gained by the system. And so you can see in D we have heat gained by the system, and then E is definitely, well, we'll see if E could be an answer. But right now it's going to be either A or D. So now we need to evaluate Q. And when W is positive, okay, work is done on the system by the surroundings, Okay, so you can see that in A, it says the system gains heat and has work done on it by the surroundings. And so that is a scenario where our Q is going to be a positive number and our W is going to be a positive number. And that's the only scenario that you could run into where the delta U will always result in a positive number. Only possibility, and so the answer will be A. Number 26, we have the table here. It says to expand at a constant temperature from a volume of 1 to 10.1 liters against an external pressure of 0.50 atmospheres. If the gas absorbs 250 joules of heat from the surroundings, what are the values of Q, W, and delta E? First, I want to just point this out. The delta E here is the same thing as our delta U that's in the Chang textbook. Again, if you look in various textbooks, sometimes they use delta E, and Chang just likes to use delta U. So if you want to call this delta U, that's totally fine. If you just want to leave it as delta E, that works for you for the problem, we can do that as well. But I'm going to switch it up and just put delta U because that's what our textbook uses. No pun intended. Anyhow, so let's evaluate our Q, our W, and from that we can determine what delta U is. How can we do that? Because we know that delta U, which we just saw in the last question, is equal to Q plus W. So as long as we tally up Q and W and we get those numbers correct, we can determine our delta U. So let's figure out what our Q and our W is. I think the easier one to figure out is the Q, right? Because Q is heat, and it says here the gas is absorbing 250 joules of heat from the surroundings. So that means if the gas is absorbing 250 joules of heat from the surroundings, Q is going to be positive 250 joules, right? Because the heat is flowing from the surroundings into the system, right? So my Q is going to be positive. And now we just need to determine W because we've already got our Q, which is equal to 250 joules. Again, all we need to do is work out our W. And we know that W, when we have the expansion of a gas, is equal to negative P times delta V. We also know that delta V is equal to the final volume minus the initial volume. Our final volume is 10.1 liters and our initial volume is 1.0 liters. When we tally that up, we end up with 9.1 liters as our delta V. And we know what our pressure is as well, because our pressure is given to us as 0.50 atmospheres. So let's plug those numbers in, and we have 0.50 atmospheres times our delta V, which is 9.1 liters, like that. Oops, and this is my number one. When we plug that in, we get W is equal to negative 4.55 liter atmospheres, like that. But we know that we're going to have to convert that into joules. And the conversion factor that we need for that is that in 101.3 joules, we have 1 liter atmosphere. And you can see that liter atmospheres are going to cancel out, and I'll be left over with joules. And in fact, I'll be left over with negative 460 joules. So let's see. We've got 250 joules for our Q, and we've got negative 460 joules for our W. If we tally all that up, we end up with negative 210 joules. Now let me see here. Negative 210. Well, the only answer could be A, where we have positive 250 for our Q, negative 460 rather for our W, and negative 210 for our change in energy. There we go. So what's the problem with this kind of question? Is it addition and subtraction and multiplication? No, absolutely not. Everybody who's hearing the sound of my voice knows how to do those things. It's interpreting the problem and understanding when Q is positive or when it's negative, understanding when W is positive or negative, and then finally knowing how to calculate W, right? That work, when we're dealing with the expansion of a gas, pressure volume work is equal to negative P times delta V. Okay, let's move on to the next question. It says here that we have 3 separate blocks of aluminum copper and iron, and they're all at 25 degrees Celsius, and they all absorb 0.505 kilojoules of heat. So they all take in the same amount of heat. But the question is, which block is going to reach the highest temperature? And we're given the specific heats of each one of these. Specific heats, the units of specific heat are joules per gram degrees Celsius. And so we're given the specific heats for each of these, and we know from our calorimetry that Q is equal to mass times specific heat times the change in temperature. Now, if we want to figure out the change in temperature, to figure out which one of these is going to have the greatest change in temperature, we can say that delta T is equal to Q divided by MS. Look, the amount of heat absorbed by all of them is the same, right? They all absorb 0.505 kilojoules of heat. No difference there, okay? They all have the same mass, right? They all have a mass of 3.5 grams. What's the difference then? The difference is the specific heat, right, times my S. So if I want to have the greatest change in temperature, right, I know that my delta T is equal to final temperature minus temperature, or the initial temperature, which is the final temperature minus 25 degrees Celsius. I'm looking for the biggest change in delta T. What's going to give me the biggest T is when the specific heat is the smallest, right? Smaller S means larger delta T, because my specific heat is in the denominator. And so this is really a conceptual question. You don't even have to do any math here. Now I've gone ahead and I've done the math already for it, but you see that copper, out of all three of these metals, copper has the lowest specific heat, which is 0.385 joules per gram degree Celsius. And if you plug copper's specific heat into this formula, and we've already answered the question, but if you plug it in, 0.385 joules per gram degree Celsius, joules per gram degree Celsius. You see I have a mishmash of units here, don't I? So let me convert the numerator to joules. So this would be 505 joules, like that. Anyhow, when you put that in your calculator, you end up with your delta T as being 375 degrees Celsius. But anyhow, again, I digress. This question is really merely a conceptual question, and you just have to know that whichever one of these blocks has the lowest specific heat is going to increase in temperature the most when it absorbs that 0.505 or 505 joules of heat. All right, that was a lot of talking on that one. I'll try to make this one a little briefer. Question 28, the total heat of hydration of 1 mole of gas phase lithium ions and chloride ions is negative 865 kilojoules. The lattice energy of lithium chloride is 828 kilojoules per mole. Calculate the heat of solution of lithium chloride, and we know that the change in the heat of solution is going to be equal to U plus the change in heat for the hydration. So hydration. And what is U? U is not energy here. U is lattice energy in this case. So lattice energy. And we're given both of those values in here. So we can calculate that the delta H of solution for lithium chloride is going to be equal to that lattice energy, which is 828 kilojoules per mole, plus my heat of hydration, which is negative 865 kilojoules per mole. And when you punch that in your calculator, you end up with a heat of solution as being negative 37 kilojoules per mole. Okay, and so that will be our answer, negative 37 kilojoules per mole, or D. Next question deals with specific heat again. We're given the specific heat of gold, which is 0.129 joules per gram degrees Celsius. What's the molar heat capacity of gold? Well, we know that molar heat capacity, which we represent with the capital letter C, is equal to specific heat times mass, or we oftentimes write it as mass times specific heat like that, because specific heat is the amount of energy that's required to raise 1 gram of a substance by 1 degree Celsius, but specific heat is, heat capacity, the molar heat capacity is the amount of energy required to raise 1 mole of a substance by 1 degree Celsius. And so we can take and use the formula. Actually, it's not really a formula. It's more just some dimensional analysis. We can say that if we have 0.129 joules per gram degrees Celsius, and we multiply that by the molar mass of gold, which is 197 grams per mole, you can see that if we plug that in, 197 grams per 1 mole, look at this, we get grams and grams canceling out, and we end up with, I should use the black pen, we end up with units of joules per mole degrees Celsius, right? Because that's what we're looking for, is the molar heat capacity. And when you multiply that out, you end up with 25.4 joules that is required to raise 1 mole of gold by 1 degree Celsius. And so the answer is E. Number 30. Given the hydrogen plus 1/2 mole of oxygen gives you water, and it gives you the change in enthalpy for this reaction as negative 286 kilojoules per mole. Determine the standard enthalpy change for the reaction shown here. This reaction, we're taking 2 moles of water, and it's decomposing into 2 moles of hydrogen plus 1 mole of oxygen. Well, what are we doing here? We've done 2 things, okay? This equation is the original that has been multiplied by 2, and it has been reversed. So that's what we're going to have to do to our delta H here. So we have to take that 286, okay, delta H, my delta H, let me fix my letter H, delta H naught for this reaction, and I'm talking about this reaction right here, is going to be equal to positive 286 because I've reversed it. And when you reverse an equation, you simply switch the sign. And since I'm doing it on twice as much, I'm going to multiply that number by 2. So I take my positive 286 kilojoules per mole, I multiply that by 2, and I get positive 572 kilojoules per mole. Again, when you reverse, you switch the sign. Okay, so we get positive 572 kilojoules per mole, which is A. Number 31, given the following change in enthalpy values for the combustion of hydrogen, which we just looked at in the last question, didn't we? And then the decomposition of hydrogen peroxide, it asks us to calculate the delta H of reaction for this interesting reaction here. Hydrogen peroxide decomposes to give you water plus 1/2 a mole of oxygen. Well, remember, according to Hess's law, the change in enthalpy is a state function. It doesn't matter how we get there. And so we can tally up these equations. And if they tally up to give us this final equation here, we can add the delta H's together for the 2 reactions. And we will, or sorry, one of them's a reaction, one of them's a delta H of formation. Anyhow, we tally them up and we will end up with the delta H for this reaction, right? Because that's what we're trying to determine. Okay, well, how would I manipulate the 2 equations that I'm given? The first thing that I notice is that I have hydrogen peroxide here, and this is the only place I have hydrogen peroxide, and I have 1 mole of it, and so I don't have to manipulate that second equation in any way. So I'm going to start out by just writing this equation unadulterated. So I'll put that down. H2O2 in the liquid phase. Remember to include your phases. Produces 1 mole of hydrogen gas plus 1 mole of oxygen gas. Let's write down our delta H, which is equal to 187.6 kilojoules per mole. So I've got that done. Now, what am I looking for? I want to have 1/2 mole of oxygen on the other side, and I've got to have hydrogen on the other side as a product. And so how am I going to manipulate the second equation? Well, it turns out that I actually don't have to manipulate the second equation, do I? Let me see here. No, I don't have to manipulate them. Now that I'm looking at it carefully, I didn't do this one ahead of time. But you see that the only place that the only way you could get rid of these two hydrogens is to have them on opposite sides. And I've already decided that I can't change this equation, and there's no H2 present, okay, in the final equation. So really, all I have to do is tally up these two equations. So let me show you what I mean, okay? If you're not 100% sure by what I mean, let me show you. When I write out that second equation, or the first equation, but I'm going to write it second, I'll have H2 gas, okay, plus 1/2 mole of oxygen gas produces water, and I'm given my delta H, which is negative 285.8 kilojoules per mole. Now, if you don't believe me that when you add these up, you're going to get the same, that reaction that's in the red box, let me prove it to you right now. Anything that's the same on both sides of the equation can be canceled out. Look at this. I cancel out both of my hydrogens because one of them is in a product, the other one is in the reactant, so those are eliminated. And what else can I cancel? Well, I can't cancel all of the oxygen, but here I have 1 mole of oxygen, and here I have 1/2. So if I cancel out my 1/2 in the reactants of the second equation that I have written, that means I'm going to be left over with 1/2 here. And so the total of those two would give me this. Maybe I should use a fancy color. It's going to be H2O2 liquid produces H2O liquid plus that 1/2 mole of oxygen gas. So that means all I have to do is tally up those two numbers. 187.6 kilojoules per mole, subtract 285.8 kilojoules per mole. And when I do that, I end up with my delta H of this reaction. Maybe I should have written in green, but anyhow, gives you negative 98.2 kilojoules per mole. And so that is our final answer. And here we have it. Give me a thumbs up if you follow me on that one. This is where we apply Hess's law. All right, wonderful, excellent. Let's proceed on from there to question 22. Much in the same vein as the last question. It's just another application of Hess's law and seeing if we can manipulate these two equations that say given in order for us to calculate the standard enthalpy change for this reaction right here. So we have 2 moles of C8H18. That's octane, like the octane that's found in gasoline. Well, 17 moles of oxygen gives you 16 moles of carbon monoxide. Plus 18 moles of H2O. I think this is a typo, isn't it? Oh, no, it's not. Okay. Everything looks legitimate now that I'm looking at it a little more carefully. Anyhow, there we go. So what are we going to do here? The first equation doesn't have to be manipulated in any way, shape, or form because the only place that I have 2 moles of octane is in that first equation. Okay, so the first equation, I'm just going to rewrite it out the same way it's written. So I have 2 moles of octane, C8H18, which is a liquid, plus 25 moles of oxygen gas produces 16 moles of carbon dioxide gas plus 18 moles of water. The delta H for this reaction is negative 11,020 kilojoules per mole. Now let's examine this thing a little bit closer. And you can see that you want to end up with 16 moles of carbon monoxide. Now, the only place I have carbon monoxide in either of these equations is right here where I'm circling in green. And so what I'm going to have to do is I'm going to have to reverse this equation, right? I'm going to have to flip the sign positive, right? When I flip it, so I'm going to have to reverse, right, the equation. And then I'm going to have to reverse the sign over here. And then if I want to have 16 moles, I'm going to have to multiply by 8. And I'm going to have to multiply by 8 over here. All right, so when I reverse that equation and multiply by 8, I get 16 moles of carbon dioxide gas produce 16 moles of carbon monoxide gas plus 8 moles of O2 gas, like that. Now, when I change the sign on 566, negative 566 rather, I just get 566. But when I multiply that by 8, I end up with, what is it, 4,528 kilojoules per mole, like that. Now, let's double check to make sure these two equations tally up to give us our overall desired equation. This one right here. Let's see. We've got 16 moles of oxygen on both sides. And I've got oxygen over here, but I've got 25 moles of oxygen here. 25 subtract 8 equals 17. Okay, so that would give me 17 moles of O2. So that would give me 2 moles of octane plus 17 moles of oxygen. Going to produce 16 moles of carbon monoxide gas plus 18 moles of water. Okay, and then I'm just going to tally up those two delta H's. And I end up with a delta H for this reaction as being negative 6,492 kilojoules per mole. I noticed that you should only have, no, that's okay. That's a correct number of 6 things that we're talking about. There we go. So our delta H is negative 6,492 kilojoules per mole. Another application of Hess's law. So you can imagine that I'm definitely going to ask you a question about Hess's law on the actual exam. All right, let's move on to question 33. Question 33 says, when 18.5 grams of mercuric oxide or mercury 2 oxide is decomposed to form mercury and oxygen, 7.75 kilojoules of heat is released, or absorbed, sorry, at standard state conditions. What is the standard enthalpy for the formation of mercuric or mercury 2 oxide? So what's happening in the reaction is this, is that you're taking mercury 2 oxide, which is a solid, and is decomposing to form mercury, which is a liquid, plus oxygen, which is a gas, and they're telling you that the delta H of this reaction is equal to 7.75 kilojoules. And you're starting out with 18.5 grams of mercuric oxide. So what we should do next is balance the equation, because you can clearly see it's not balanced. I have 2 moles of oxygen in the product, so I need to have a 2 here, and then I need to balance that out with a 2 there. Now, we know how many kilojoules are absorbed. How many kilojoules, how many kilojoules are absorbed when we do this decomposition reaction, okay? This is a decomposition, okay? But it's asking us about the standard enthalpy for the formation of mercuric oxide. The formation of mercuric oxide, right, the delta HF naught of HGO is going to be the formation of that compound from its elements, right? So that means we're going to start out with mercury, which is a liquid, plus oxygen, which is a gas, and we're going to form mercuric oxide, or mercury 2 oxide, which is a solid. Look familiar? It's this equation here. It's simply reversed. Okay, it's not balanced, but it's simply reversed. If I balance it out like this, you can simply see that it's a reverse. So as long as we figure out the delta H of the decomposition per mole of mercuric oxide, then we'll be able to say, well, if we just reverse that, that's going to give us the formation of mercuric oxide from its elements. Okay, So what do we need to do next then? Is we need to determine how many moles of mercuric oxide we have. And we know that in 18.5 grams of mercuric oxide, since the molar mass of mercuric oxide is 216.59 grams per mole, and I went ahead and calculated that already, we know that we have 0.0854 moles of HGO. So that tells us that our delta H of our reaction is equal to 7.75 kilojoules per 0.0854 moles of HGO, right? So that tells us that the delta H of that reaction in terms of moles is 90.7 kilojoules per mole. And so if I reverse that, when I do my delta H of formation, all I have to do is flip the sign. And that tells me that my delta H of formation is going to be negative 90.7 kilojoules per mole. And what do you know? The answer is here. It's E. Number 34, how much heat is evolved when 4.50 grams of iron 3 oxide is reacted with excess carbon monoxide according to the equation shown below? Well, let me rewrite the equation because I always hate it when they kind of squeeze it there in a multiple choice. So we have iron 3 oxide, which is a solid, plus 3 moles of carbon monoxide, which is a gas, producing 2 moles of iron, which is a solid, plus 3 moles of carbon dioxide, which is a gas. They give us the delta H of the reaction, which is negative 24.8 kilojoules per mole. But I'm using 4.50 grams of iron 3 oxide. Is that a mole of iron 3 oxide? Definitely not, because 1 mole of oxygen weighs 16 grams per mole, so that's impossible. In fact, I've gone ahead and I've calculated the molar mass of iron 3 oxide already, and it is 159.69 grams per mole. So what does that tell us? Okay, what does that tell us? Well, if we know the number of grams per mole, or the molar mass of iron 3 oxide, and we know the mass of iron 3 oxide, we can figure out the number of moles of iron 3 oxide. Okay, because number of moles is always equal to mass divided by molar mass. So we have 4.50 grams divided by 159.69 grams per mole. Look at this. Grams cancel out. I'm left over with moles, and I have 0.282 moles of iron 3 oxide. And now what I need to do is determine the amount of heat evolved. I'm kind of running out of space here, so I'm going to move this a little bit like that. And then I'm going to say my heat evolved in this reaction is equal to negative 24.8 kilojoules in 1 mole of Fe2O3, right? Because we have 1 mole of Fe2O3 in our equation, okay? And I know that I'm actually reacting 4.50 grams, which is 0.282 moles of Fe2O3, iron 3 oxide. Those units cancel, and I'm left over with the amount of heat that's released when you burn up that, or when you when you put that 4.5 grams of iron 3 oxide in this reaction. And the amount of heat that's released is negative 0.699 kilojoules, like that. And so here's our answer right here, E. Now, something I've just noticed here, because I'm like, well, that's not the same as what I put, is since they're telling you in the question that heat is evolved, that means that it must be negative, right? It must be a negative number. So that's why they've listed all these numbers as just positive quantities, because they're saying how much heat is evolved. So it stands to reason that I ended up with a negative number, but that negative just means that it's evolved, okay? So instead of saying negative, you could just say evolved, okay? Get produced by the reaction, nothing more than that. Okay, let's move on to number 35. Where are we? Given the specific heat of aluminum, I like to write, sometimes I just love to write things down right away. I can't wait. It is 0.900 joules per gram degrees Celsius. How much heat is released when a 3.8 gram sample of aluminum cools from 450 to 25 degrees Celsius? So for this, we're going to need the formula, the heat released, Q, is equal to mass times specific heat times our change in temperature. We're given the mass of our aluminum, which is 3.8 grams. We're given our specific heat, which is 0.900 joules per gram degrees Celsius, and we're given our delta T. Remember that delta T, just like delta V or delta E, is equal to TF minus TI, like that. So our final temperature is 450.0 degrees Celsius. Our initial temperature is 25 degrees Celsius. I've gone ahead and done the math already on this one because I think it's pretty quick. And when you calculate that Q that's evolved, you get 1.7, because we can only have two sig figs, 1.7 times 10 to the 3 joules. And you notice that that isn't one of the answers, but you see that a couple of the other answers are listed in kilojoules. And we know that in 1,000 joules, we have 1 kilojoule. Joules cancel out, and I'm left over with my final answer, which would be 1.7 kilojoules, and that is an answer. It is C, 1.7 kilojoules. Number 36, if 10.6 moles of water absorbs at 35 degrees Celsius, absorbs 12.30 kilojoules, what's the final temperature of the water? They give us a specific heat of the water. Well, for this problem, we're going to use the same formula we did in the last one, that Q is equal to M times S times delta T, but we're just looking for the final temperature. And so we can rewrite this as Q is equal to the mass, our Q is equal to mass times specific heat times TF minus T initial, like that. We know our Q, which is 12.30 kilojoules. I'm going to go ahead and convert that into joules. So I multiply by 1,000 joules in 1 kilojoule, like that, and I end up with 12,300 joules. Oh, yeah, I'm getting tired. Anyhow, so we have our Q, which is 12,300 joules, is equal to our mass, which is, oh, jeepers, I didn't calculate the mass of the water. How are we going to calculate the mass of the water? Well, we're given the number of moles of water. So from that, we can simply use the formula that mass is going to be equal to number of moles times molar mass. So let me just do that quickly. Now I have 10.6 moles of H2O, and I know the molar mass of water, which is 1 mole of H2O has about 18 grams of H2O. That's close enough. Close enough for jazz, right? So let me go ahead and do that. So 10.6 times 18, it's 18.01. So this is going to be fine. We'll put in 191 grams. I know I'm going from 2 sig figs to 3, but again, since 18, it's so close to 18.0, we'll just say it's 191. So we have 191 grams multiplied by our specific heat, which is 4.184 joules per gram degrees Celsius. Then I have my TF, that's what I'm looking for. Subtract my T initial, which is what? 35 degrees Celsius. I'm running out of space here, aren't I? Let me see. Tuck this away down here, maybe. Okay, so when I take 12,300 and I divide it by 191 times 4.184, I get 15.4. So I get would be what? 15. It would be 15.4 degrees Celsius, wouldn't it? 15.4 degrees Celsius is equal to TF minus 35 degrees Celsius. So I get that my TF is equal to 15.4 plus 30. I should be able to do that in my head. That's 35. Oh yeah, so it's going to be 50 degrees Celsius. There we go. Good enough. And there's the answer, 50 degrees Celsius for that one. Okay, just a little bit of algebra, right? Nothing super intimidating, just a little bit of algebra on that one. Number 37, find the change in enthalpy for this reaction, which is the combustion of methane. So we have methane plus oxygen gives you carbon dioxide and water. They give us the heat of formation for what? They give us the heat of formation for methane. That's good. They give us the heat of formation for carbon dioxide. That's good. They give us the heat of formation for water. Also good. Why do they not give us the delta H of formation of oxygen? How come they didn't give us the heat of formation of oxygen? Can anybody answer that question for me? And it's not a trick question. Why wouldn't they give that to me? It's a missing information here. Or do I? Well, the answer is the most stable form of oxygen, exactly, is O2, right? Ozone, which is O3, is not the most stable form of oxygen. And so the delta HF of oxygen is 0. Now I'm just going to throw in units because I like to, but 0 is 0. It wouldn't matter what the units were. So we have a delta HF formation of oxygen is being 0. Now you might remember this equation that the delta H naught for a reaction is equal to the sum of the stoichiometric coefficients multiplied by the delta HF of the products, okay, minus the sum of the stoichiometric coefficient multiplied by the delta H of formation of the reactants. And so when I plug in the numbers for this, let's see, I'm going to have to use a lot of brackets here for my products. So I'll start with my CO2. I have negative 393.5, and I only have 1 mole of that, plus my water, and I have 2 moles of that. So that's going to be 2 times negative 285.5. Close all that up. Okay, close it up in a big bracket. Subtract, and I can see that I'm running out of space here. But anyhow, for my reactants, I have my methane. I only have 1 mole of that, so negative 74.8. And then plus 0, because the heat of formation for oxygen is 0. So I do all that. And then outside of all this, I'll just put kilojoules per mole as my units. And so let me tally all this up. And you end up with negative 964.5, subtract negative 74.8 kilojoules per mole. You subtract a negative, it's like adding it, and we end up with negative 889.7 kilojoules per mole as the change in enthalpy, the standard change in enthalpy for that reaction. And we're talking about this reaction right here, and there's our change in enthalpy for that reaction, which is negative 889.7 kilojoules per mole. Okay, 38. Find the heat that's absorbed from the surroundings when 15 grams of oxygen reacts with, according to the equation shown here. So we have oxygen, an oxygen atom plus oxygen gas produces ozone. We're given our delta H naught of reaction is being negative 103 kilojoules per mole. And let's see here. It says heat absorbed from the surroundings. Well, if it's heat absorbed from the surroundings, the way that delta H is written, it says that this is an exothermic reaction, right? So if we do this in using 1 mole of oxygen atoms plus 1 mole of oxygen gas to produce 1 mole of ozone, the heat that's released by this reaction is 103 kilojoules per mole. But it's asking us how much is going to be absorbed from the surroundings. And so to know how much would be absorbed from the surroundings, all we would have to do is reverse this reaction, right? All we would have to do is reverse it, change the sign. I'm not going to bother doing that. I'm just going to change the sign of my delta H reaction after I figure out how many moles of oxygen I have in 15 grams. So let's start by determining the number of moles of oxygen, which is going to be equal to the mass divided by the molar mass. I have 15 grams divided by 32.0 grams per mole for O2. my units of mass cancel, and I'm left over with the number of moles, which is 0.47 moles of oxygen. And so if my delta H naught of reaction is equal to negative 103 kilojoules per 1 mole of O2, and I'm multiplying by 0, or I'm reacting 15 grams, so that's 0.47 moles of O2, right, because that's what we calculated. We can see that moles of O2 cancel out, and I'm left over with the amount of heat that's produced, right, that's going to go into the surroundings, okay, which would be negative 48 kilojoules, like that. Now remember, it's telling us absorbed from the surroundings. They've given us an exothermic reaction, but if we change the sign, it becomes an endothermic reaction, okay? So the answer has to be a positive number, and it would be positive 48 kilojoules, like that. Okay, question 39, the combustion of 1 mole of benzene, C6H6, in oxygen liberates 3,268 kilojoules of heat. The products from the reaction are carbon dioxide and water. How much heat is given off when 183 grams of oxygen are reacted with excess benzene? The first thing we're going to need here is a balanced equation. We're starting with our C6H6, which benzene is a liquid, and we're combining it with oxygen gas. We're producing carbon dioxide, which is a gas, and we're producing water. Put water vapor here. It does, the state of matter isn't really important here for the water. It's actually probably water liquid, but whatever. Anyhow, let's balance this out. Let me show you how to balance a combustion equation. Always start by balancing out the carbon. We have 6 carbons in benzene, so we're going to have to put a 6 in front of carbon dioxide. The second thing you do is balance hydrogens. Here we have 6. Over here we have 2. What times 2 gives me 6? The answer is 3. Then you tally up all of the oxygens here. So I have 2 times 6, which is 12. 12 plus 3 is a total of 15. And so here I'm going to put 15 over 2, like that. Now, I know that usually we don't like to leave fractions in our equations. And so we can multiply this whole equation by 2 to eliminate that fraction. And we end up with 2 moles of benzene. It's going to react with 15 moles of oxygen to produce 12 moles of carbon dioxide and 3 moles of water. But you know what? I'm going to back up, and I'm just going to leave it the way it is because it's perfectly fine. There's no reason why we can't do the stoichiometry with a fraction in there. Okay, so I'm reacting 183, excuse me, 183 grams of oxygen, and I want to know how much heat's going to be given off, okay? Well, of course, I'm going to need to determine the number of moles of oxygen because my stoichiometric coefficients describe the number of moles. I know that for every 1 mole of benzene, I consume 15 divided by 2, or 7.5 moles of oxygen. So let's figure out the number of moles of oxygen. And I know that in 1 mole of oxygen, I have 32.0 grams of oxygen. And you can see that my units cancel beautifully. And I end up with the number of moles of oxygen as being 5.72 moles of O2. The next part is just going to be a little teeny tiny bit of dimensional analysis. If we have 5.72 moles of oxygen, and we know that for every 15 over 2, right, 15 over 2 is equal to 7.5. So we know that for every 7.5 moles of oxygen, we consume 1 mole of benzene. And we know that when we burn 1 mole of benzene, C6H6, we liberate 3,268 kilojoules of heat. Looky, looky. Moles of benzene cancel, moles of oxygen cancel, and I'm left over with the amount of heat. Let me see, 5.72 divided by 7.5 multiplied by 68, and I end up with 2,492 kilojoules, like this. Now remember that the 7.5 moles here, that's an exact number. but this number here only has 3 significant figures. And so our final answer should have 3 sig figs, so it should be 2,490 kilojoules. And that is what's released when we burn that 183 grams of oxygen in the presence of excess benzene. And so our answer is 2,490 kilojoules. All right, we've made it to the last question. Number 40, the heat of neutralization of hydrochloric acid by sodium hydroxide is negative 56.2 kilojoules per mole. How much heat is released when 125 mils of 1.75 molar HCl is mixed with 195 mils of 0.667 molar sodium hydroxide? First thing we're going to do here is we're going to write a balanced equation, because we know that when we take 1 mole of HCl and we combine it with 1 mole of sodium hydroxide, we produce a salt, sodium chloride in this case, plus water. Okay. Now we know that we're starting out with how much HCl? We know that we're starting out with 125 milliliters, which is the same thing as 0.125 liters. So I have 0.125 liters, and I'm multiplying that by 1.750 moles per liter. So that gives me the number of moles of HCl. And the number of moles of HCl, when I punch that in my calculator, is 0.219 moles. Again, you can see how volume cancels out. Now let's do the same exercise for our sodium hydroxide. We're told we're starting with 195 milliliters, which is 0.195 liters. So we have 0.195 liters multiplied by 0.667 moles per liter. Liters cancel, and we're left over with the number of moles of NaOH as being, and I've done this already, 0.13. Let me see here. 0.195 times 0.667. So 0.130 moles of sodium hydroxide. Since the ratio of sodium hydroxide to sodium hydroxide is 1 to 1, if we examine these two, you can clearly see that sodium hydroxide is the limiting reactant. So NaOH is the limiting reactant. Okay, and so we know that if the delta H of this reaction is negative 56.2 kilojoules for every 1 mole, and you can see that you have 1 mole of sodium hydroxide, so we could even write for 1 mole of sodium hydroxide, and we're using 0.130 moles of sodium hydroxide. Well, looky, moles of sodium hydroxide cancel out, and we're left over with the amount of heat that's released when we mix these two acids together, and that is going to be equal to negative 7.31 kilojoules. So that's how much heat is released when you combine those two solutions together. Now again, it says released, and so the negative sign denotes released. So since they're saying that the heat is released, you don't need a negative sign in the answer, and so the answer is 7.31 kilojoules for the combination of those two solutions together.